Video number 2 on sequences. So we are now going to take a look at the limit of a sequence. So as it says, a fundamental question that arises regarding infinite sequences is the behavior of the terms as n gets larger and larger. So in other words, as n approaches infinity, a limit, what is happening to the terms of the sequence? Are the terms of the sequence approaching some number, L, which we would call the limit, or are they not approaching any number? In other words, they're getting infinitely large or infinitely small. So if the terms of the sequence are approaching some number, some value, which we'll call the limit, L, we say that it is a convergent sequence. It converges to L, and L is the limit of the sequence. If there is no value of L, in other words, the terms of the sequence are just getting larger and larger and larger and larger and larger, or smaller and smaller and smaller, then we say it's divergent and there is no limit. And so there's a few techniques for finding limits of sequences, and so we have to recall some work that we did a long time ago with limits. And I have to apologize, I made a mistake in this first problem, so I didn't see that when I did the problem, but I saw it when I started making the video. So, first of all, here is our sequence written out as an explicit formula. And so we want to simply take the limit of the sequence as n approaches infinity. So one of the first things that you learned about limits and the limit properties is that you can split the limit if there's an addition and subtraction. You can split the terms of the sequence into their own limits. So we have the limit of 5 minus the limit of 3 times the limit of 1 over n squared. So we're basically just taking the limit of each term there. Now, the limit of any constant is the constant. So that was one of your limit rules. And if you need to, you can go back and refresh your memory as to why the limit of any constant is just the constant. So that's 5. And this is where I made the mistake. The limit of 1 over n squared is 0. And so here's the thinking that you have to go through to get that. As n is getting infinitely large, think about this. The numerator is staying the same. Numerator is 1. It does not change. But the denominator is getting larger and larger and larger and larger and larger. As n gets infinitely large, the denominator is getting infinitely large. It's getting infinitely large. And if the denominator is getting infinitely large and the numerator is staying the same, this whole quantity approaches 0. So that's an important thing to be able to understand and remember that we'll be using a lot in this chapter. So 0 times 3 is not 3, it is 0. And so 5 minus 0 is 5. So the limit is 5. And so since this limit is 5, we say it is convergent. All right, it is convergent. All right, the second one is another technique that we're going to use. You have a polynomial function in the numerator and a polynomial function in the denominator of your sequence. And so one technique that is very useful to use when evaluating the limit of polynomial functions like this, which are actually rational functions because it's the ratio of two polynomial functions. So you have a rational function, is to take the highest power of n, which in this case is n to the fourth, the highest power of n in the numerator or the denominator, and divide every single term by that power of n, which is n to the fourth. So I divided each term by n to the fourth. When you do that, here the n to the fourths cancel. You end up with just 3. Here the n to the squared and the n to the fourth cancel out. You end up with an n squared in the denominator. In this one, nothing cancels out, so you just keep it as it is. Nothing cancels out here. And in here, the n to the fourths cancel, so you have 4. So now it's a little bit easier to actually take the limit. So going back to what I just explained to you in the last problem about this right here, we're going to use that knowledge again to find the limit here. So the limit of 3 constant is 3. And so as this denominator gets infinitely large, the entire fraction goes to 0. Same thing with this. This goes to 0. Same thing with this. This goes to 0. And then the limit of the constant is the constant. So what we end up with is a negative 3 over 4. So once again, this is convergent. All right. Now, I made a couple mistakes in this one too. So the limit of a sequence defined by a function. All right. There's absolutely no difference between what we just did and what we're doing now. The only difference is if you are looking, you want to find the limit of a sequence. Well, if you create the limit of a function, in other words, the only difference is whether you have an n or an x. If I write 2 to the x over x squared, that's a function. Okay, f of x is equal to 2 to the x over x squared is a function, but this with the n's is a sequence. That's the only difference. But we can find the limit of them exactly the same way. Okay. In other words, if we wanted to find the limit of a function, defined as a function, we just find the limit. So I wrote this in terms of n's. It should have been written in terms of x's. So that was my bad. All right. So it should have been 2 to the x over x squared. All right. So we actually are going to use L'Hopital's rule. If you remember L'Hopital's rule from Calc 1, to find the limit of a function, we can use L'Hopital's rule. So using L'Hopital's rule, remember we take the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator for 2 to the x, the derivative of 2 to the x is 2 to the x log of 2. This is my second mistake in this problem. This was a bad morning, I guess, when I was doing these. So 2 to the x times the log of 2. So this comes from the derivative. If you have b to the x, the derivative of b to the x is b to the x times the log of b. All right. So then you take the derivative of the denominator, which is, of course, 2x. So here is the first permutation of L'Hopital's rule. Well, I still really can't take the, I could take the derivative, but let's make it even easier, okay? Because we got x's in the numerator, we've got x's in the denominator here. And so to figure out if it's converging to something, you have to determine, is the numerator getting infinitely large faster than the denominator is getting infinitely large? And, it's kind of a little hard to tell sometimes. But it'd be easier if you simply took the derivative again. So remember, you can apply L'Hopital's rule multiple times. So the derivative of 2 to the x log of 2 is 2 to the x log of 2 squared, and the derivative of 2 to the x in the denominator is just 2. Well, this makes it easier. We just have an x in the numerator. And so when x is getting infinitely large, this whole quantity is approaching infinity, which means the whole numerator is approaching infinity, which means the whole thing is approaching infinity. So we are not approaching some value L. We're approaching infinity, which means this is a divergent sequence. Anytime your answer is plus or minus infinity, it is divergent. All right, here's one that's similar to that. You might recognize the outcome here. So, taking the limit And again, I put n's in here instead of x's, so I changed these to x's. We're taking the limit of that, and I'm also just letting that be equal to y. Let y be equal to the limit as x approaches infinity of the quantity 1 plus 4 over x to the x power. Well, in this case, there's a nice little trick. You take the log of both sides. So you take the log of y, and you take the log of the limit. Then there's a limit property that says if you have the limit of a log, you can take the log of the limit or vice versa. So all I'm doing here is switching the log and the limit. Instead of taking the logarithm of the limit, I'm taking the limit of the logarithm. Yes, you can do that. There's a property that lets you do that. Okay, now there's another property of logarithms. Now that this is a logarithm in here, remember there's the power property of logarithms, and the power property of logarithms says when you have a logarithm and the base is being raised to some power of x, you can bring the x out in front, or whatever that exponent is. So that x comes out in front, so it's x times the log of 1 plus 4 over x. That gets rid of the exponent, makes it a little bit easier to deal with. So again, we're using limit properties and logarithm properties. Now, how did we get to this? Okay, well, I'm kind of thinking I'm going to have to use L'Hopital's rule again. But L'Hopital's rule applies to fractions, all right? You have a numerator and a denominator. And so this does not have a denominator. So what we can do is we can rewrite it by taking this x and dividing it by 1 over x. Because remember, dividing by 1 over x would be the same as multiplying by x. And so that's how we get this. Now we can apply L'Hopital's rule. And I will let you figure out that I didn't show the work here, but if you take the logarithm, the derivative of this logarithm, you take the derivative of 1 over x, that whole thing is going to simplify to this, okay? So from here to here, it is applying L'Hopital's rule very carefully and canceling out some factors and reducing it to 4 over 1 plus 4 over x. I'm sure you guys can do that. All right, now taking the limit as, I didn't actually need this here again, another mistake. So taking the limit of 4 divided by 1 plus 4 of x. As x gets infinitely large, this whole term is approaching 0. So we end up with 4 over 1 plus 0, or 4 over 1, or just 4. All right? So what we have is the log of y is equal to 4. Now, let's change that. Let's solve that for y. To solve that for y, we switch it from logarithmic form into exponential form. So we take the base, which is e, raise it to this power, and set it equal to the argument y. So there's a lot of stuff in there. There's L'Hopital's rule, there are limit rules, logarithm rules, changing logarithms to exponential functions. So there's a lot of math that you have to remember in addition to just the new material. Okay, so that's going to be common in this course. Calc 2 is one of those courses that, as you've already seen, integrates pretty much everything you've ever learned. All right, one more thing for this video. We always have to talk about the Squeeze Theorem. The Squeeze Theorem, if you have 3 different sequences, consider the sequences A sub n, B sub n, and C sub n. Now, suppose there exists an integer n such that B sub n is less than C sub n, but greater than A sub n. In other words, it's between those two for all n greater than or equal to n. Don't get too confused about that. There exists a real number L. There will be a limit where the limit of A sub n is equal to L, the limit of C sub n is equal to. In other words, if the limit of this function and this function or sequence are both L, then this is being squeezed in between them. So if we I'm gonna just draw a little sketch of what what might look like, an example. So if you had one function that's doing this and another function that's doing this, they're both converging to 0, okay? So here's my a sub n, here's my c sub n, and they're both converging to 0. So the limit of a sub n is 0. The limit of c sub n is 0. Now let's suppose that what it's saying is that b sub n is between those two for all values of n, for every term of the sequence. That means whatever b sub n is doing, it's always in between these two functions. It's never going to go outside those. So as a sub n and b sub n are getting closer and closer and closer to 0, then b sub n has to get closer and closer to 0. It's being squeezed in between these two. And since the limit of a sub n is 0 and the limit of c sub n is 0, the limit of b sub n must also be equal to 0. Okay? Because it's always in between those two functions. Okay, so let's look at two quick examples. And again, a more detailed analysis of this can always be found in the textbook. So here is our sequence, and the numerator is the cosine function. Well, what we know about the cosine function is that the cosine is always between -1 and 1. All right? So cosine of any function is always less than or equal to 1, greater than or equal to -1. And so if we just take this relationship right here, okay, and we're basically divide each one of these by n squared, okay? In other words, we're dividing both sides, all three sides of the equation by n squared, then we get this right here. And now let's take the limit of this. Well, the limit of -1 over n squared is 0. The limit of 1 over n squared is 0. So since the cosine of n over n squared is always between these two functions, and these two functions are converging to 0, then it's just like the example that I gave you above, where b sub n, the sine function, is going to be going up and down, but it's being squeezed in between those two functions. And so the limit of this function is going to be equal to 0. Now the next one is pretty much similar to that. If you take a look, if we take our sequence and we squeeze it between something that's similar, what we're always doing is we're looking for something that's similar that we know what the limit is. So -1 to the n is like -1 to the n over 2 to the n. So that's another way that we could write this, -1 to the n over 2 to the n. So the numerator is alternating. The numerator is alternating in sign between positive and negative. So the denominator is 2 to the n. It's getting larger, but the numerator is always shifting back and forth between -1 and +1. So that means that the numerator is always going to be between +1 and -1. So again, to write this, nicely, to rewrite this a little bit, we can rewrite this as -1 to the n over 2 to the n, which is less than or equal to 1 over 2 to the n, but greater than or equal to -1 over 2 to the n. The denominators are all the same. Keep the denominators same. And we know, again, the numerator here is shifting between these two numbers. All right, so once again, just like the last problem, we can show that the limit of this and the limit of this are both approaching 0. And so therefore, the sequence that we have squeezed in between the two of them is also approaching 0. Now, these don't have to be approaching 0. All my examples, they have. That's typical of a lot of examples. But they could both be approaching any number. If they were both approaching 2, then the limit of our sequence would be squeezed towards a limit of 2. Okay, I believe that is it for this particular video number 2.